sum of the powers. So here are some examples. The NOBr breaking down into NO and bromine, and hydrogen and iodine making hydrogen iodide. If you write down the rate laws for second order reactions look like this. The change in concentration over the change in time, the rate, is equal to K, the rate constant, times a concentration squared, second order. Or the rate is the product of two concentrations. So the sum of the powers, 1 plus 1, gives you second order kinetics. If you write that rate law versus time, it looks like this. 1 over the A concentration is given by 1 over the initial concentration plus KT. So a plot of 1 over concentration versus time is linear. And that's how you determine if you have a second order chemical reaction. You measure concentrations versus time, then you take 1 over the concentration and you plot it versus time. If that's linear, then you have a second order chemical reaction. Now we can look at the half-life for second order reactions as well. The half-life goes as 1 over the initial concentration times the rate constant. So the initial amount, the initial concentration matters in terms of the half-life. The amount of time it takes to go from initial concentration 2 molar down to initial concentration 1 molar depends on the fact that it's 2 molar. That is, it's going to take longer for 4 molar to go to 2 molar than 1 molar down to half molar. And that tells you something about the kinetics. A second order reaction means there's some collision somewhere in there. It's dependent on the concentration squared, the interaction of the particles. It's dependent upon two concentrations, the concentration of A and B, or the concentration of hydrogen and iodine. Those have to come together. If the concentration of iodine